Thank you very much. And thank you all for coming to my talk, even though it's like quite late in the conference. I hope you have enjoyed it. I will talk about a project together that I did together with Renato Renner that appeared on the archive a couple of months ago, which is about commuting operations factorize, as the title says. So the question that we're looking at is the following. Basically, we ask the question, when can we say that we have a subspace structure on a Hilbert space? So in quantum information processing task, a very typical scenario we're looking at is usually like we have two parties, Alice and Bob, that perform some sort of quantum information protocol. And then to describe it mathematically, we assign a Hilbert space to Alice, we assign a Hilbert space to Bob, and then talk about a tensor product Hilbert space where the protocol is going on. Okay, but what is the justification that we can actually make this assumption? Because the tensor product structure of a Hilbert space, that's not something that we can experimentally test, right? Initially, all we have is some global Hilbert space H, where all the operations, all the quantum systems, where everything's happening. Okay, so, but while we cannot test the structure of the Hilbert space, we can test other things, and from that infer what kind of structure our Hilbert space has. So for example, what we can test is whether two operations on this Hilbert space commute. We can design some experiment that tests this. And then we can make we can get some information about the structure of the Hilbert space from our observations. And as the title suggests, what we can infer from commuting operations is that the Hilbert space factorizes. So putting it differently, the question is, when can I justify that I have this Hilbert space structure in my quantum information processing protocol, starting from a global Hilbert space where Alice and Bob are acting on? Okay, so let us make this question a bit more precise. And I want to model this, that Alice and Bob act on this Hilbert space in terms of completely positive trace-preserving maps, X and Y. So X describes the action that Alice does in this Hilbert space, and Y describes Bob's action. So we have this Hilbert space H here. That is one input to these maps. And also Alice and Bob each have an input system and an output system for these maps. And generally, all these systems are quantum. So also the IJ and the AB, the input-output systems, everything here is quantum. Okay, so this is how we describe what Alice and Bob are doing on the Hilbert space. So what do I mean when I say this factorizes? So what it means is that we can write these maps as a tensor product of maps instead of performing them one after the other. And as you see here, it's not enough to just write the maps as a tensor product, because we need two copies of this Hilbert space. So in addition, we need some map that comes before, which we call the doubling map, which just gives us two copies of this Hilbert space. And basically, its job is to distribute the information in the Hilbert space accordingly to the information that Alice needs and the information that Bob needs, so that afterwards, these tensor product maps, they can act on the respective information on the Hilbert space they need. Okay, so this is what I mean by factorization. And it's kind of clear when we see that, like when we write these maps as a tensor product, that the minimum condition that needs to be fulfilled, such that we can have any hope that this holds, is that the maps commute. So the maps shouldn't affect the part of the Hilbert space of the other map. Otherwise, there's no hope to write them in this tensor product form. And commutation, well, it means the obvious thing. I can just put the maps in the other order. Okay, so in terms of these pictures, the question we're asking is, does the left-hand side imply the right-hand side? So when I can write these maps in any order, does it imply that I can actually write them as a tensor product? All right, so to address this question, what we start with, we look at what do we already know about this case. And we already know something about the classical case. And by the classical case, I mean that these input-output systems, I, J, A, B, that these are classical systems. Of course, we're still operating on a quantum system, on a Hilbert space. But now I, J, A, B, they are classical systems. And this is known as Tsyrilson's problem. He posed this, the question that I will phrase now. And if the input and output systems are classical systems, well then the operations that Alice and Bob perform, they are measurements on the system. And here in the setting, we're looking at independent projective measurements that describe Alice and Bob's operations. And they in particular have the property that they sum up to the identity, which we will need later in the talk actually. Okay, so yeah, you can see if these these systems are classical, then I and J, they actually describe the choice of measurement for Alice and Bob, and A and B are the classical outputs. All right. So now if we want to describe the input-output correlations of the scenario, then what we can do here, because the measurements are independent measurements, they commute, so I can just calculate this probability with this formula, and it doesn't matter in which order I apply these operations. A different way of looking at this is, of course, that instead of looking at commuting projective measurements, I say that I make a bipartition of my Hilbert space and assign one system to Alice, I assign the other system to Bob, and now I look at tensor product measurements. Those are also independent measurements on the quantum system. And then I can write these probabilities with these tensor product measurements. And Alice's measurement is only on the HA system and Bob's is only on the HB system. Okay, the question that Cyrilson then posed is, well, do these two strategies actually give the same probability distributions? If I describe all the probability distributions with this strategy, do I get the same set of probability distributions with both? And we can phrase this description of these projective measurements in terms of the maps I showed you before, the one we're looking at, by just checking how it appears in these maps. So the CPTP map, it would take a classical state on the I system, which determines the projective measurement that is applied. It takes a quantum state, applies the corresponding measurement, and puts out the classical output on the A system. So this would be the description of what's going on in terms of the maps. Okay, so then the question Cyrilson asks is, okay, what if I have commuting maps that describe projective measurements? Doesn't imply that I can write it as a tensor product. And he didn't only pose this question, he also answered this question. And he found that if the dimension of the Hilbert space is finite dimensional, then in fact, this holds. There exists an isometry such that the projectors on the global Hilbert space, they are mapped to projectors on the tensor product Hilbert space. So if you would translate it back into these maps that we're looking at, then you would get a map of this tensor product form. Okay, so does that mean that commutation implies factoring? Well, I mean, the title kind of suggests that this holds, right? But I haven't been fully honest with you in the title. It's actually not that simple. So to see that, let's look at a different, also classical example, which is PR boxes. So PR box is such a box. It takes two classical systems as an input and puts out two classical outputs, such that the product of the inputs equals the sum of the outputs modulo 2, and the outputs are uniformly distributed. Okay, and these PR boxes, they violate the CHS inequality with a maximum value of 4, because they deterministically produce these output correlations. Okay, so let's see what we can learn from these boxes about our problem. So can we find commuting maps X and Y that implement these PR boxes? Well, it turns out actually we can. And to see that, first let me emphasize that these boxes, while they have classical in and outputs, we don't say anything about how the inner workings are. So in particular, this means the box is allowed to act on some quantum system to achieve its task. So I allow some Hilbert space also as an input here. And the Hilbert space we need to implement these maps is actually a purely classical one. It's of this form, it has two different kinds of states. Either there's this one designated state, or the other states are just tuples of bits. Okay, and with this I can now define the maps that I need. So if the maps act conditioned on what type of input they get. If the input is this designated state, the map will just draw a random bit. and output it to the output system, and it will give the information about its in and output to the next map via this Hilbert space H. That means if the map, here the blue one, it sees instead of this designated state, it sees a tuple, it will calculate its output bit such that the such that this condition is fulfilled, because it has all the information it needs. It knows the in and output from the previous map. So you can quickly check that actually the output bits now fulfill this condition, that they're equal to the product of the input bits. So it's not that hard to find maps that implement this. You just have to check that they're actually commuting maps. But you see, the map acts conditioned on what type of input it sees. So it knows whether it acts first or second and acts accordingly. So in the second picture, if this X map acts in the second place, it sees that it got a different type of input and will accordingly produce the correct output bit instead of drawing a random bit. You can, like, there are some subtleties that you have to go through all the cases to see that actually commutes, but you can make the calculation and figure out these are actually commuting maps that implement the correct correlations. Okay, so we have found commuting maps that implement the PR boxes. At the same time, we know we cannot write them as a tensor product because that would violate Tsirelson's bound. Like, if we could write them as a tensor product, then we could play the CHSH game with these boxes. And as I said before, they reach a CHSH inequality violation of 4. But as Tsirelson showed, the maximum value you can reach with quantum mechanics is 2 square root 2. So this shows us there's no way we can write the PR box as a tensor product. So in this case, commutation apparently doesn't imply factorization. So what did Tsirelson actually show? He must have shown something like commutation plus some additional condition implies factorization. And the question is, what is this additional condition? Well, in his description of the problem, Tsirelson didn't allow for arbitrary CP-TP maps. He specifically said it's projective measurements that are happening. So his result is actually that commutation plus projective measurements that describe these maps, that implies factorization, plus that the Hilbert space has to be finite dimensional, but this part actually was lifted to some extent by a later work from Scholz and Werner. Okay, so our question was, like, we want to look at the case where it's purely, it's quantum in and output. So far we had classical input and output systems, and now we want to generalize this to quantum inputs and outputs. That means we have to, so we call this the fully quantum Tsirelson problem. Now we need to figure out what are the conditions in the fully quantum case such that commutation plus something allows factorization. Okay, so this was what Tsirelson said, commutation plus projective measurements, and the commutation property is that translates directly to the quantum case. But the thing is, what is this projective measurement? What's the corresponding condition in the fully quantum case that we need so that we can imply factorization from the commutation? And to see what the condition should be, we look at what in the classical case, what it actually means, like how does the projective measurement affect what how the maps look like. And this was how the maps were defined. And then you can see, if you look at the case where you put in something proportional to the identity to the Hilbert space, and you trace out the classical output system, then you actually get something proportional to the identity out. You see, here if you trace out the output system, you only have this term in the output, and your state, it's proportional to the identity. So since the measurement operators, they sum up to the identity, here in total we get something proportional to the identity. So the projective measurement condition in the fully quantum case then corresponds to this unitality condition, we call it. So if you have something proportional to the identity as an input, and you only look at the output of the Hilbert space, you get something proportional to the identity. So this is the missing condition that we need to actually get factorization from commutation of the maps. And now it's interesting to look back and see how did PR boxes actually fail this condition? Why didn't it work for the PR boxes? And if you look at the definition of the PR box, it was this, that if you get this designated state as an input, you do something and you output a tuple. And in the other case, you also output some tuple. You see what is going wrong. So putting the identity into the Hilbert space here, since it's a classical Hilbert space, it corresponds to putting in a uniform distribution on the Hilbert space. But in the output, you see, you will always get a tuple of some form in this Hilbert space, and you never get this designated state as an output. That means the probability for this designated state is 0, hence you can never get a uniform probability distribution out. So in this way, the PR boxes fail this unitality condition, and hence we cannot get, our theorem doesn't imply the factorization of them as it shouldn't. Okay, so with this I can summarize the main result of our paper, which is that if you have commuting maps, still with finite dimensional input spaces, and your maps satisfy this unitality condition, then you can imply factorization for these maps. So this was the missing condition we need in addition to commutation to be able to imply factorization for the maps. And interestingly, we also got a converse statement for this. So if you have a map that you can write as a tensor product, then you can find maps, commuting maps, that fulfill this unitality condition, such that you can write it in this way, which tells us that the unitality condition is really necessary. There's no way we can prove this without the unitality condition. Okay, and I think I have a few minutes to quickly say something about the proof idea behind this. So basically what we did is we looked at the Choya-Minkowski state of this map, and then we used the commutation property and the unitality of the maps to show that the mutual information between the system belonging to Alice, the input and output system, and the systems belonging to Bob, conditioned on the Hilbert space. This mutual information is 0. And then we used the result of Hayden, Josa, Petz, and Winter that implies that when this mutual conditional information is 0, then your state has this tensor product structure. So it's a sum over a tensor product of states. And then you can go back, use the Choya-Minkowski isomorphism backwards to obtain the factorized maps. Okay, so that's the basic idea of the proof behind this. Yeah, and as an open question that we're now looking at after we have shown this result is there actually a robust version of this? So can we start with some approximately commuting maps and get approximately an approximate factorization of these maps, given that the unitality condition also holds? And this is something this robust version is something you might think, why do we need to go to the fully quantum version of the Tsirelson problem? From Tsirelson's problem, you already get some factorization for your Hilbert space. But the thing is, if you want a robust version like this, you have problems when you look at classical input and output systems. Because you see, when you look at classical probability distributions, if the probability distribution factorizes for all measurements you do in a quantum state, then you can infer from that the quantum state has product form. But this doesn't hold any longer if it's only approximate. If your probability distribution only factorizes approximately, you cannot infer that your quantum state has approximate tensor product form. So for that, one would need to look at or possibly need to look at the fully quantum version of this problem. Okay, and with this open problem, I thank you for your attention.
Questions?
Thanks for this interesting talk. I have got a few questions. So the first of which is, why is it that we are not allowed to use Neumann extensions to think that we can take projective measurements for granted in this case? And the second question is related. So are you saying that if I take this commuting operators framework, and if I do not impose the conditions of projective measurements, then I could actually have a way of realizing the PR box correlations.
Okay, I'm not sure I understand your questions correctly. So in the first one, what do you mean with the extension? Because what we're looking at is just general CPTP maps in this setting.
I mean, if I
Oh.
so you mean the first questions? Oh,
Yeah,
or the
the first of your questions.
so you're saying that what Zerosyn has shown actually also require this assumption that the measurements are projective.
Yes.
So I'm just wondering, I mean, if we
Okay, now I think I get your question. So you mean, for example, if I had POVMs instead,
yes,
I think it should still hold with the POVMs. That wouldn't be a problem. Yes.
right.
Mhm.
So you're saying that okay, so you're considering something that's more general. It's not
Yes. Yeah.
not just measurements,
Yeah.
but
Exactly.
there's some way to map to some output so that it has
Yes.
this
Yeah.
kind of
And the output could be quantum in our case, but
okay,
the thing with the POVMs and the projective measurements is, in some sense, they behave well in the
Right.
sense that they don't change the output state on the Hilbert space more than necessary, right? Because in principle, what an operation could do is do a measurement and then also perform some unitary or something, do more with the output state on the Hilbert space than just measuring it. And by describing it with projective measurements or POVMs, you ensure that the operation is well behaved in some sense.
okay, all right, okay. I think that sort of answers my second part as well. Thanks.
Okay, great.
Hi, thanks for the nice talk. So if you see this, I mean, I saw some of your motivation is sort of deriving the tensor product structure. But it seems to me that you're still assuming the tensor product structure for the inputs versus the sort of here, the white lines versus the orange line. Do you see a way to get around that too?
Yes, actually in the paper, the statement is more general. It starts with just one input Hilbert space and has conditions on that the maps are independent of certain parts of the Hilbert space. But yes, you still need some sort of subsystem structure on this input. So the conclusion is just that on the Hilbert space, the part you didn't assume anything, you get something. If I see a way to get around that, I'm not sure. I mean, somehow you need to talk about, I think that these maps are independent of certain parts of the Hilbert space, but maybe one could replace it with like a different condition that doesn't need a specific structure, but we haven't thought about that so far.
Okay, thanks.
Thanks for the nice talk. I just wanted to ask about the converse direction.
Yes.
Was the statement that if you have some maps that are factorized, then you can always find a representation of them with commuting operators that is unital, or that every such representation has to be unital?
Well, we find it's a constructive proof actually. So we get the exact form of the maps you find on the other side, the commuting ones.
And they have to be unital, or just you give an example of some that are unital?
No, they have to be unital. They always fulfill this condition that they always have this property that they're unital.
Even if the original maps aren't unital themselves?
Okay. No, that's what you mean. No, I think these maps that you put in here, they have to be unital, yes.
Okay. Thank you.
I have a couple questions. One is just, I think, a point of confusion. When you talked about the PR box and you represented it as a sequence of two commuting operations, you only checked the commutation on a specific input for the Hilbert space, which was the perp state. In general, I think when you write commutation on the left diagram, you mean for every state of the Hilbert space.
Yes.
So are you thinking that this Hilbert space kind of expands, or does it also hold for?
No, it holds for all inputs.
Okay.
I just haven't shown that here because the other inputs are not so necessary for the PR box. But yes, we did the calculation in the appendix of our paper, but they commute for all inputs.
All right, thanks. And for this question, so I was wondering, so there's some famous examples of, for example, unitary matrices that are very close to commuting. That approximately commute, but are very far from commuting unitary matrices. So do you know about this? And wouldn't it give a counterexample to this question? So this is the case, I'm thinking the case where I and j are trivial. There's just a Hilbert space. X and y are just unitaries, and they approximately commute, but they're far from commuting. So in particular, they're far from anything in tensor product.
Yes. Yeah, so I know vaguely about that, so we haven't looked into this direction so far, but we know that there are some results that will give constraints to what's possible at all. So it's very possible that the approximate statement wouldn't hold like this, but we need to add maybe more conditions on the left-hand side to get an approximate factorization.
Yeah, that example would give you a dimension dependence in the in the epsilon on the right-hand side, based on the epsilon on the left-hand side.
Yeah.
Okay. All right. Thanks.
Sort of more of a comment maybe than a question. Are you aware of the work by Schumacher about metanomic reference frames and partial metanomic reference frames that could probably be related to this robust version, where they essentially consider like the reference frame information required to tensorize some Hilbert space?
I'm not aware of that work, actually. So thanks for pointing it out.
Yeah.
I will certainly have a look. Thank you.
Sure.
Well, hi. So I also have small comments. I think there's a paper in 2004 from PRL where I think the title is something like tensor product structure is observable induced or something like that. And they also discuss a very similar problem, but I think they approach this problem using operator algebras. Are you aware of this work?
Okay, I don't know that work very well, so I think I can't comment on that. So.
Yeah, thank you for the nice talk. I'm just going back to the unitality condition again. Do you think it might be able to weaken it by using a different version of the Choya-Miaskovsky in the proof? Because you don't need to use the maximally mixed state.
Yes. So what we think is what might hold is that we don't actually need unitality, but it suffices that the maps have full support, because that would also rule out the PR box counterexample. And we have a suspicion that this might be enough, but we haven't seriously tried to prove that yet.
Okay, because you need the faithful state for the Choya-Miaskovsky.
Yes.
So that sounds believable. Yeah, thanks.
Yeah. Also, I'd say thank you for the fascinating talk, and also for the unitality condition. So the way you showed the PR box, it looks very much like it's just signaling from Alice to Bob or from Bob to Alice. So I guess this is somehow capturing the essence of no signaling. I just wanted to check if that's the right intuition here.
Yes, yeah, I think that's some way to think about it, yeah.
Okay. Maybe related, maybe it's a very slightly technical thing, but I have a kind of an optical illusion that, so when we use, say, NPA to find bounds on Bell inequalities, we are assuming a commuting framework, and there we know we can derive Sirelson's bound, for example. And so but we don't seem to implicitly use this unitality condition. So I just wondered how I put everything together, or do you know, or?
Yeah, that's a good point. I think I have to think about that more to answer that. Yeah.
Thank you.
Okay, no more questions? If no, let's thank